Hello, everyone. Here I'm going to demonstrate my ECE 5831 final project CNN model, OK versus not OK binary classification using Python. So in this project, I will go through how I imported the libraries and the framework and go how I build the model, loaded the data set, and trained the model, finally predicted the model and tested the results on new images. So let's start. I'll just demonstrate the steps. So first, I will discuss the project really quick. So basically, this is a CNN application project to classify hood outer mastic stitches. So it basically tells the system if a product is okay or not okay based on if the stitches of if the mastic stitches is presented on the part, which is the hood outer panel, or is not presented. So I'll start with importing the libraries here. So I've used TensorFlow and Keras to build my architecture. I also imported OS to locate the path of my folders. And finally, I've also imported Matplotlib to plot the images. And I've also imported confusion matrix and classification reports to build the classification or the confusion matrix of the predicted images. So I've used an image size, which is assuming a square image size of 224. This is what I've used. I've used 32 numbers of images to be processed in one batch. 32 is the numbers of images, and I used epochs, 10 numbers of training epochs. So this is just a step that I used to inspect if the directory of my folders is working properly. So this shows the training directory and the test directory contents. I have not OK folders and OK folders in each folder. The next step is I loaded the data set from the directory, and I used the load data set function here to load the images from the train folder and the test folder, and then added the classification names so that I can allow the model to understand the labeled OK, not OK for each image. And I just added the return function here to use those data set later when we train the model. So this just shows that the images are loaded to the system. So here it shows numbers of images that are loaded. Here's the OK, not OK mastic stitches application. As you can see, the not OK is very similar to the OK. So this is a difficult classification item, but its results were very promising. So next, here's what the architecture we built. So I used the Keras architecture. So first we've added the layers input of 32, using 32 layers, 32 filters, and I applied a max pooling after the first layer to reduce dimensions. So it would reduce computation time. And then I used 64, and that's in the second layer section, and 128 in the final one, all with max pooling between them. I flatten out the images so that I can have an array of pixels with brightness configuration in each pixel. Finally, use the dense fully connected layer with the 128 neurons to activate an output. And the last thing is I use sigmoid. So this function gives us an activating function that gives us the output layer with 1 or 0 based on the binary classification. I used the Atom optimizer, which is an optimization algorithm to help the the model based on the highest influence to the model. So it's a good optimizer for training methods. I've also used the binary cross entropy loss function. So this basically penalizes the system or the model when it predicts an output and that output is not correct, but the accuracy of that output is very high. So this is when binary cross entropy is used. So basically, it penalizes the system to adjust that weight significantly since the accuracy was high, but the prediction was wrong. So the fourth step is where I trained the model. So as you can see here, I let me build the architecture first. Here's what the architecture that I built. And then step 4, I trained the model using 10 epochs. So this will take a little bit of time, just about maybe 15 seconds for each epoch. I have 10 epochs, so this will take about 150 seconds. As you can see here, the accuracy increases after each epoch, and the loss, entropy loss decreases. Validation accuracy also increases with more epoch is trained. So as you can see here, we're very close to 100% accuracy. It's about 80, 86, 84, and now it's 92, 94, 96. Hopefully we'll get to the 100 in this run. Finally is the 100. So I didn't want to go more than 10 because sometimes when you go more than 100 accuracy, the system starts to memorize images more than learning them. So it's a good rule of thumb to just stop the numbers of epochs when your model accuracy hits 100%. Now I plotted the training results to just a good slides for the presentation. So here's the accuracy increases by the numbers of epochs, and the loss decreases by the numbers of epochs. Here I tested the model just to evaluate and see the confusion matrix on each of the models. So over here we have basically 44 actual not okay images that are predicted okay, and about 56 okay images, and all of them were predicted okay. So none of them was predicted not okay. We have about 94 recall accuracy, and I have 100% not okay prediction with a 90% okay prediction. So it's about 98 to 96% accuracy overall. Here I've tested the model on a new images just to test the model and check the accuracy. So in the first run, I have testing one okay image and see if it actually tested correctly. So let's run that. Here we have an okay image and the accuracy is about 95%. This is correct. Here, let's test a not okay image. So this is a not okay application of mastic stitches on the hood outer. So application shows a not okay prediction, and probability of that stitches or that application being okay is 0.03%. So pretty low, very good accuracy. So here's just testing all the images at one time, randomly selected. So I didn't want to select all the 200 images, but this would select quite a few numbers of images. And as we can see here, this is okay, because as you can see here, the stitches are connected to each other. So this shows that it's an okay stitch. This is an okay stitch as well. This is okay. This is not okay. As you can see, the stitches are far away from each other and not applied properly by the robot. This one is okay. As you can see here, this is one of the failed results. As you can see, the accuracy is not that high. Probability of it being okay, 0.6 only. This is a not okay part, but it's predicted as okay. So this is completely fine, but this is why we will improve the system with next steps. Here's an okay part. This is a not okay part. So this is correct. There's an okay part. And this is all again is a not okay part. So this is also good. And that's it. So that's my final project demonstration for hood stitches application with an okay and not okay classification. I've used a PY, a Python script, just to train the model only. And then I've used a Python script just to evaluate the model. And finally, I've used a Python script to uh, test and predict the model. So basically the same thing that we went through in the IPYNB file is just split into three different Python scripts for easier use and classes segmentation. So that was my demonstration for this final project. I hope you enjoyed it. If you have any questions, please let me know. My email is abugamea@umesh.edu. Thanks a lot for watching.